Imagine an AI that actually knows when it's stumped,
Yeah.
when it's out of its depth, and it can tell you clearly how sure it is or isn't. Today, we're doing a deep dive into, well, a really fascinating new mathematical framework, one that promises exactly that, making AI humble.
Hmm.
And this isn't just about, like, AI being polite or anything. This humble AI idea, it tackles some huge problems in AI right now.
Absolutely. We're talking about, the massive costs, the resource drain, and maybe most importantly, this issue of overconfidence we see everywhere.
Right.
So yeah, we'll be digging into this really interesting paper, an entropy-optimal path to humble AI, plus some related stuff.
Yeah.
And we'll show how this whole new approach could be a really powerful and actually surprisingly efficient alternative to the AI models most people know.
Okay, so our mission today is basically to pull out the key ideas from all this pretty complex material. We want to help you understand not just what this humble AI thing is, but crucially, why it really matters for the future, especially for you trying to make sense of it all. So let's maybe unpack this a bit. A lot of the AI making headlines, right?
Yeah.
Deep learning, LLMs, they often lean on things like feed-forward networks, backpropagation, gradient descent.
Yeah, the usual suspects.
These have obviously led to amazing things, but you mentioned downsides. What are the potholes, so to speak?
Right, potholes is a good word. Because while they are incredibly successful, these methods, the gradient descent ones, they definitely have drawbacks. Pretty big ones, actually. First off, costs. Just astronomical. The paper calls it huge and further exploding costs and resources.
Wow.
Yeah, training means, numerically crunching this loss function down, often needing a huge number of steps. Massive compute power needed.
Yeah.
Very expensive.
And it's not just the raw cost of running the machines, is it? I hear getting them to work well is tricky.
Oh, absolutely. That leads straight into the next headache,
Yeah.
hyperparameters. Getting
Yeah.
good results means tons of tweaking, usually just trial and error with things like batch size or learning rate scheduling.
Right, those knobs you have to turn.
Exactly. And sometimes, the more advanced the algorithm, the more knobs there are to tune. It can be a real nightmare for engineers, honestly, just finding that sweet spot.
Okay, so it's costly, it's finicky to tune. What about the data? Don't they need tons of it?
That's the third major issue, yeah. The big data trap. Modern neural nets typically need large amounts of data to perform well. If you don't have that, or if your data is really high dimensional,
What happens then?
they tend to overfit. Basically, they just memorize the training data perfectly, but they can't generalize. Ask them something slightly new, and they're lost.
Like rote learning versus actual understanding.
Precisely.
Okay, now this next one feels really crucial, especially for trust. The confidence problem. You're saying current AI will just give an answer for anything.
Pretty much, yeah. They typically define their decision functions across the entire input space. Doesn't matter if the input is totally alien to what it was trained on.
And they don't tell you they're guessing?
Generally, no. They usually report no confidence metric related to how far a test point is from the training data. So this leads to what the paper calls a lack of robustness and overconfidence, which is exactly why things like adversarial attacks work so well.
Ah, right, where tiny changes completely fool the AI.
Exactly. Tiny, imperceptible changes can make a model flip its decision, often with high confidence. It's confident even when it's demonstrably wrong or just guessing wildly.
Okay, that's unsettling. So before we get to the humble AI fix, you mentioned another path, energy-based models. What's the background there?
Yeah, it's helpful context. Energy-based models offer a different kind of foundation. Think of them less like a signal flowing forward and more like a system settling into a low-energy state, kind of like physics.
Like Hopfield networks. Weren't they about memory?
Exactly. Hopfield networks were inspired by neuroscience, trying to model associative memory remembering patterns. They used ideas from statistical physics, like an Ising model, calculating a system's total energy. Then came Boltzmann machines, BMs. They built on Hopfield networks, added hidden units, and used stochastic units, probabilistic activations. That let them learn probability distributions, which was a big step.
And then restricted Boltzmann machines, RBMs, made them easier to train.
Right, RBMs were a simplified version, more efficient. They could learn probability distributions, do unsupervised learning, generate data. Quite powerful.
But they still had issues, right? What was the bottleneck?
Yeah, they hit a wall too. Training them using something called contrastive divergence involves this expensive approximation of the negative gradient. Basically, the math gets crazy hard, growing exponentially with the number of units. So you get slow convergence and expensive computations.
Ah, okay, so still computationally heavy, just in a different way.
Exactly. which is why for many things, they've been largely superseded by other approaches. They were promising, but just too slow or difficult to train effectively for really big problems.
Right. So that brings us back to EON, the entropy-optimal network. This is the paper's proposed solution, the humble approach. What makes it different?
Okay, so EON, yes. It's framed as a novel reformulation of Boltzmann machines, but it makes some really fundamental changes. Core innovations, you could say.
Like what?
Well, first, it's deeply probabilistic. It extends those energy-based ideas, but allows each state to be a whole probability distribution, not just on or off, 0 or 1.
So it's dealing with uncertainty from the ground up.
Precisely. It uses specific probability conforming distance measures
Yeah.
and the exact law of total probability. It's built to handle probabilities rigorously.
And you mentioned it gets around some limitations of older models.
Yes. Crucially, it relaxes the equilibrium assumption that constrained traditional Boltzmann machines. This gives it more flexibility, more ways to tune it.
Okay, but here's the big one you hinted at. No gradient descent. How?
Oh, this is the absolute game changer. The beauty of EON is that it finds analytical solutions. It completely sidesteps backpropagation and numerical methods based on gradient descent.
Wow, so what does that mean practically?
It means, like the paper says, no tuning the respective gradient descent-related numerical algorithm parameters like learning rate, momentum parameters, batch size, etc.
No more hyperparameter headaches.
Exactly. Think of the time saved, the frustration avoided. It leads to straightforward and cheap analytically computable steps. You're not guessing anymore. You're calculating directly.
That sounds almost too good to be true for anyone who's wrestled with training models.
It's a massive shift. And it's not just convenient. EON comes with mathematically justified existence and uniqueness criteria for its solutions.
Meaning
You get a level of robustness and predictability you just don't often see. It's mathematically solid, not just a complex black box you hope works.
okay, let's get into the weeds a bit. How does EON actually work? You said layers, like other networks.
Yeah, think of it as layers, but with this probabilistic twist. It starts with an input layer. This layer takes your raw data and turns it into probability distributions. But crucially, it also measures the reliability of the inputs.
Reliability.
It compares your input data to a set of learned reference positions. It's like asking, how similar is this new data point to the kinds of data I was trained on?
So it's already assessing familiarity at the very beginning.
Yes. Then you have the subsequent layers, the entropic layers. These layers transform the probability distributions from the layer before, again, using the exact law of total probability. The goal here is to minimize an expected cross-entropy functional, basically making sure information flows efficiently while respecting the probabilities.
And each layer has constraints.
Right, expected entropy constraints. These can be tuned, and that's part of what allows the model to work beyond the equilibrium assumption we talked about. Gives it more flexibility.
Okay, so how does it learn if there's no gradient descent nudging weights up and down?
The learning process is really elegant. It combines the losses from the layers and these entropy constraints into one objective function. Then it uses what's called a coordinate descent algorithm instead of tiny steps for everything at once.
Like gradient descent.
Right. Instead, coordinate descent focuses on one set of variables at a time, say the reference positions in the input layer, and finds the exact analytical solution for them while keeping everything else fixed.
Oh, I see. Like perfecting one piece before moving to the next.
Exactly. Then it moves to the next set, like the transition matrices between layers, finds the exact solution for those, and so on. It cycles through until everything is optimized.
And this works better.
Well, it's monotonic, meaning the overall loss function is guaranteed to always decrease or stay the same with each step. You don't have the problem of under or overshooting the local loss optimum that can plague gradient descent.
And computationally.
Each step has a polynomial time complexity. So, while it's iterative, it's computationally much more predictable and often faster than waiting for gradient descent to converge, especially since you avoid all that hyperparameter tuning.
Okay, this brings us back to that really appealing feature, the confidence measure. You said the input layer handles this.
Yes, that's where EON really shines in terms of, well, humility, I guess. That initial probability distribution it calculates for the input, they call it 0, gamma 0, that acts as an input reliability function.
So O0 is the key.
It is. Think of it as EON's built-in confidence score generator.
How does it work? What does it tell you?
It gives you a reliability score indicating how far each point on the evaluated grid is from the training data,
Okay.
measured in the dimensions that were found to be relevant for this problem. Simpler terms, It tells you how much the new data is similar to the training data examples.
That's fantastic. So it knows when it's seeing something weird or unfamiliar?
Exactly.
Yeah.
And this is huge because, quoting the paper, such measures of input reliability are not available in the common NN tools. It directly tackles that overconfidence problem.
So you won't just confidently classify something it's never encountered before.
It will classify it, but the DEAR score will tell you, hey, I haven't seen much like this before, so take this prediction with a grain of salt. It knows what it doesn't know.
And can this help with those adversarial examples you mentioned?
Yes, interestingly, EON can be used to find adversarial points
How?
by looking for the inputs that result in the most uncertain classifications, the lowest reliability, the highest entropy in the output. This is super useful. You can use it to guide data collection, saying, we need more data right here where the model is most confused, or just understand the model's weak spots better.
Okay, the theory sounds incredibly promising. Efficient, analytically solvable, provides confidence. But how does it actually perform? Did they test it?
Oh, yes. They put EON head-to-head against standard methods, neural networks, NNs, random forest gradient boosting, RFGB, and even a transformer model specialized for tabular data called tab-PFN.
How did it stack up? Let's start with synthetic data, maybe, controlled tests.
Good place to start. So they had this bioinformatics-inspired problem. Some input features were useful, others were just noise. EON's decision function learned to essentially ignore the noisy dimensions.
Smart.
NNs, on the other hand, showed noise due to the dependence on the 4 non-informative dimensions. They got confused by the irrelevant stuff.
And the model size? You said EON was efficient.
Get this, EON's model size was just 15 parameters. That almost perfectly matched the theoretical minimum complexity for that problem, the Kolmogorov complexity, which was 13 parameters.
Yeah. Bare bones.
Exactly. The best NN they found, 401 tunable parameters. That's 26 times higher. Plus, EON converged significantly faster.
Okay, that's a striking difference. What about other benchmarks? More dimensions?
They use benchmarks called stacked Gaussians and rotated rings, testing different complexities and going up to 300 dimensions. EON consistently hit accuracy values close to 1. NNs and RFGB often struggle to generalize as well on these.
And speed, size.
EON was often around 2 orders of magnitude faster than NNs and RFSGBs for both training and evaluation.
2 orders of magnitude. That's huge.
It really is. And again, the EON models were consistently on the boundary of the Kolmogorov complexity, KC, of the problem. Super compact, getting straight to the essence, while the others were much larger.
That's impressive on synthetic data. But the real test is messy, real-world stuff, right? Did they try it on something like climate? You mentioned El Nino.
Yes, predicting ENSSO phases El Nino and La Nina is a classic complex challenge. It's irregular, has huge global impacts.
How'd EON undo?
It systematically showed higher prediction skills for the onsets of both El Nino and La Nina compared to the others.
Okay, better predictions. What about the data requirements? Climate models usually need tons of historical data.
This is maybe the most stunning part. EON needed just few years of climate data for training a small fraction of what is necessary for contemporary climate prediction tools.
Just a few years. Seriously.
Seriously, it highlights how good it seems to be for small data learning problems, even when you have lots of features, like in climate science.
So it learned more effectively from less data.
Exactly. And even when predicting further out longer lead times, EON performed on par or superior to the other state-of-the-art methodologies, while still having smaller models and faster training.
Okay, this really does sound like a potentially big deal. Bringing it all together, what are the main takeaways for someone listening to this? Why should they care about humble AI?
I think there are a few really key takeaways. First, efficiency. EON lets you train more compact models in less time, often getting better prediction performance. That's huge. Faster results, less compute needed, big win.
Makes AI development more accessible, potentially?
Definitely. Second, interpretability and trust. That input reliability measure is a game changer. It directly fights AI overconfidence. Getting a confidence level with predictions is crucial for explainable decisions in sensitive fields, right? Like climate research, healthcare, and other areas. You need to trust the output.
That built-in skepticism, knowing what it doesn't know.
Yeah, that seems vital. Third, small data, big impact. EON seems to be a significant step towards solving small data learning problems. It works well even when dealing with high feature dimensions and relatively small sample data statistics. That opens doors where data is scarce, but insights are needed.
Right, not everything is a big data problem.
Exactly. And finally, maybe the underlying point, mathematical elegance. Using analytical solutions instead of endless gradient descent tuning just makes the whole process more robust, predictable, and understandable. Less guesswork, more solid math.
Yeah, this whole dive into entropy-optimal networks, it really does make you rethink things. We're always hearing about bigger models, more data, more power.
Hmm.
But maybe the path forward isn't just about scale. Maybe it's about being smarter, more efficient, more, well, humble.
I think that's a great way to put it. This work suggests that by going back to some fundamental mathematical principles and maybe building in that humility from the start, we can actually get better performance. And crucially, we can also gain the transparency and trustworthiness that we increasingly need as AI becomes more embedded in critical parts of our lives.
So here's a final thought to leave you with. In a world that feels like it's drowning in data, maybe the most powerful AI isn't the one that processes the most information. What if it's the one that truly understands the limits of its own knowledge? The one that knows what it doesn't know?
Something to think about.
Join us next time for another deep dive into the fascinating world of knowledge and insights.